All right, welcome back. So where were we here? When I had to run off and get a cough drop. As you can see, I'm kind of nursing a cold here. So essentially, why can we lump the entire red box of reactions into one rate? It looks like there's a branch point here, fructose 1,6-bisphosphate. Well, we can do this because the fate of hydroxyacetone phosphate, at least in the pathway we're considering here, is just interconverted to glyceraldehyde 3-phosphate. And it's just going to continue in the glycolysis pathway. So this is essentially a linear pathway, all of it, from glucose 6-phosphate, or from intracellular glucose really, all the way to pyruvate. So we can consider that as one big linear rate here. And that's what we will do. So we simplify our pathway diagram here, and we make some assumptions. So we assume that glycolysis intermediates are not being used for biosynthesis or growth in this case. We also assume that glucose to pyruvate can be considered a linear sequence, which is for the reasons I just said. And we assume thus that the individual glycolytic reactions are grouped into a single reaction step with the rate of V1. And our major branch points are at pyruvate and acetyl-CoA, right here in the middle. And acetyl-CoA to acetate and acetyl-CoA to ethanol are linear sequences that can be lumped into two grouped reactions, like we said earlier. So we write down our we begin our flux balance by writing down our stoichiometries. So we go from glucose all the way through lactate, acetyl-CoA, formate, acetate, and ethanol. We also include an ATP to ADP balance. We write down our mass balances with our rates for all of the different compounds that are involved: glucose, pyruvate, lactate, carbon dioxide, formate, acetyl-CoA, acetate, ethanol, etc. So now we can determine our degrees of freedom for this scenario. F, of course, is our degrees of freedom. J, as I mentioned before, the number of reaction fluxes, our R's and our V's. And K is the number of metabolites that we're considering in these reaction fluxes here. So we determine our degrees of freedom here. We have 7 internal fluxes. If you look back on the map here, you can see, you can count, or you can assure yourself that there are 7 internal fluxes hanging around there somewhere. And there are 6 external fluxes, either substrates coming in or products going out. That gives us a total of 13 rates. So in our case, J, or R as it's sometimes known, equals 13. There are 10 metabolites that we are considering here, all listed right here. Our K, or our M, as it were, is 10. So F equals J minus K, or R minus M, whatever you want. 13 minus 10 gives us 3. We have degrees of freedom of exactly 3. So is the system here, is it overdetermined, underdetermined, or exactly determined? Well, let's look at the rates that we have. Our degrees of freedom is 3. So we have 3 measured rates, as it turns out. So we have our Rg, our rate of glucose uptake, our rate of lactate efflux, and our rate of formate efflux. Therefore, with our number of measured rates equal to F, the system that we are looking at here is exactly determined. This is an exactly determined system. So getting an answer is going to be fairly straightforward. So we can do that vector math. We can separate our vectors. We have our vector of measured fluxes right here, which includes our RG, our RL, and our RF here, and there's the numbers. And then our stoichiometric coefficient matrix SM here. So we have those. Of course, we have our SC, our negative SC. So essentially what we will do is be able to solve for VC, because we can invert SC, and then we are pretty much done. So we have a vector of calculated fluxes, which at this point are all just variables because we haven't solved yet. Here is our vector of coefficients. Right here, our SC. SC is non-singular, which is important. The matrix calculation software, i.e. MATLAB or something like that, can be used to determine the inverse of our SC and get our SC minus 1. Here is our SC minus 1 right here, the inverted vector. And thus we can do the matrix math. We have our SC to the minus 1, we have our SM, we have our VM. We multiply these things together, and we end up getting all of our internal rates here in this vector. We populate them with numbers, our V1 all the way to V7, our RC, our RA, and our RE. Here they all are in units of moles per gram per hour, because that's what we started in, is units of moles per gram per hour. We can turn those into rates of C-moles per gram per hour by just multiplying each of the rates by the number of carbons involved. So if we're looking at glucose, we can multiply by 6. Pyruvate, we multiply by 3. If we're talking about lactate formation, we multiply that by 3. CO2, we just multiply by 1, etc., etc., etc. And we can turn those into C-moles per gram per hour. So we can solve our metabolic flux analyses rather easily, provided that all of our equations are linearly independent. We talked about the rank of a matrix earlier. So none of the algebraic equations is a linear combination of other equations, which we found out here. Mainly we found out because it worked. But the SC matrix has full rank. The matrix can be inverted, and then we can solve for our VC. No problem. However, in the cases of SC having a rank that's less than our K, the matrix is singular. We talked about it being non-singular. It is singular, and a solution cannot be found, so we can't go any further. We are dealing, in essence, all of a sudden, with an underdetermined system. So what do we do about that? What do we do if our SC matrix has a rank of less than K? The rank may be smaller than K for two reasons. We've got to first find out why it is less than K. The set of reaction stoichiometries could be linearly dependent on each other. There could be some rows that can be written as a linear combination of other rows. We'll see an example of that. The measured rates were chosen in such a way that the rank of SC is less than K. We'll show an example of that also. In that case, some of the measured rates are redundant. So that's going to cause us a problem. Both of those result in what essentially is suddenly we have an underdetermined system. Either we've measured the wrong rates, or we are looking at reaction stoichiometries that end up being linearly dependent to each other. And how does this happen? Well, first let's talk about dependent stoichiometries. There are a number of reasons that in metabolic flux analysis we could be faced with linearly dependent reaction stoichiometries. There are common issues where this occurs that a lot of tales have been told about this. One is the glyoxylate cycle in prokaryotes. Again, this is key central metabolism stuff here. Nitrogen assimilation, either via the GS-GOGAT or the GDH. The presence of transhydrogenases that affect the NAD-NADH balance. Or the presence of isozymes that basically different enzymes that do roughly the same thing. Let's use the example of the glyoxylate cycle, the TCA cycle and the glyoxylate cycle. So if we examine amino acid production, this all tends to come off the central metabolic pathways. So the TCA cycle is probably going to be involved. Potentially also the glyoxylate cycle could be involved. The glyoxylate cycle is basically a shorter version of the TCA cycle. It's used to assimilate acetate and such. And it uses a lot of the same enzymes that the TCA cycle does, but it actually goes through an intermediate that's called, oddly enough, glyoxylate. So we have the TCA cycle, the glyoxylate cycle, and an enzyme called pyruvate carboxylase that converts pyruvate to oxaloacetate. So if we examine the balances for these three pathways, the TCA cycle, the glyoxylate cycle, and the pyruvate carboxylase, we see there's a lot of similarities here. We are all dealing with pyruvate here. Pyruvate is the substrate, one of the main substrates, as is and carbon dioxide is also present. And in a couple of cases, oxaloacetate is our product. If we consider GTP to be ATP, if we consider them equivalent, not too far a stretch there, and we don't worry so much about NADH and FADH2, then it becomes obvious that equation 2, or pathway 2, equals 1 plus 3 here. So we got some redundancy going on. We must eliminate one pathway in order for our metabolic flux analysis to go forward. But which one should we do? First, let's think of some things here. It should be noted that TCA cycle and glyoxylate cycle rarely operate at the same time in bacteria. For example, the isocitrate lyase, which is the first enzyme in the glyoxylate cycle, is repressed by many organisms when they grow on glucose. In other words, when their TCA cycle is active. Also, if we're talking about eukaryotes, the TCA cycle operates in the mitochondria, and the glyoxylate cycle operates in the cytosol. So they're compartmentally separated. So they aren't necessarily redundant. They're not dependent on each other because they're occurring in two different spots. Another example, we have the glutamate synthase and GOGAT system. The ammonia assimilation can occur by either glutamine dehydrogenase, this GDH, or by glutamate synthase GOGAT system. So we have these two systems here. We've talked about them previously, where we have the substrate is alpha-ketoglutarate and ammonia, and we have glutamate as the product. And one system uses ATP, one does not. So aside from ATP, the stoichiometries are the same. Thus, they are linearly dependent. There are two routes of the ammonia assimilation to make amino acids. They are often just lumped into one reaction in stoichiometric models, as opposed to being two separate and dependent reactions, or at least in terms of the metabolic flux analysis. So, this brings us to what do you do when singularity arises of your matrix. You can remove the linearly dependent reaction. You would have to do that by invoking information about specific enzyme and pathway regulation and induction. For example, our TCA cycle, glyoxylate cycle. You could introduce additional information, such as relative flux of the two pathways, or relative activities of isozymes, things like that. But if you're doing that using enzyme activity measurements, you need to beware, because often, if not always, in vitro measurements do not often mirror in vivo conditions. It is usually best to use a labeled carbon substrate and determine the distribution of label among products and intermediates if you're going to go this route here. Alright, so back to our example. Lactic acid bacteria are often grown on a complex media. There's peptides, there's amino acids that provide carbon skeletons and building blocks. In this case, they're growing quite well. They've got a lot of good stuff to eat. Bacteria only use the pathway from glucose to lactate. This is known as homofermentative metabolism. And essentially we can see it here with the blue arrows. They're taking glucose and they'll make lactate out of it. However, under extreme starvation conditions, lactic acid bacteria will try to squeeze out a little more ATP from their glucose. It's in their best interest to do that because they're not dealing with this nice, lovely, rich media that they used to have. So thus, they're going to produce other acids like acetate, formate, etc. And a little ethanol is going to be produced as well. The ethanol is mainly to combat the redox imbalance. So from a metabolic flux analysis standpoint, pyruvate becomes a major branch point here. You can see pyruvate will give us lactate, but it's also going to give us formate, CO2, and that acetyl-CoA, which is again a good branch point and intermediate to get our ethanol and our acetate. So thus, when we do our MFA, our metabolic flux analysis, we need to pick our measurements. What are we going to measure? We can solve for the calculated rates. Like we did earlier, we chose the RG, RL, and RF, the rate of glucose influx, the rate of lactate, and the rate of formate efflux as our rates. The RG can help us determine the rate of formation of pyruvate, or R-pyr, which is basically equal to 2RG. Using these rates, we can solve for the other calculated rates, like we did. But what if we measure different rates? Let's say we measure our RG, a rate of glucose formate, or a rate of glucose influx, our rate of acetate formation, and our rate of formate formation. We would get an SC matrix that looks a lot like this. You will note that row 3, this row, basically equals row 1 plus row 2 here. So these reactions are linearly independent. So what does that mean? How does that reflect what we just did in real life? How does that translate into real life? So RG, the real reason, the real life reason that RG, RF, and RA cannot be used is that they're not giving us any information. You can see RG is here, RF would be right here, and RA, they're not giving us any information on NADH consumption. NADH consumption is happening either with lactate formation, with acetaldehyde formation, or ethanol formation. So we would need to, we would need to consider RL or RE really. RC not necessarily. It doesn't give us any information about consumption, only of NADH formation. And we need to know what's going on with consumption. So we're just not, our balance isn't closed, shall we say. So we picked the wrong measurements in order to close our balance. That was not a good idea of us. Okay, so metabolic flux analysis can allow us to calculate rates of carbon flow through many different pathways. What you need to get started, the stoichiometries, and we need measured rates, some measured rates. Hopefully you have enough so you can make an exactly determined system. The degrees of freedom will tell you how many of those you need to get that exactly determined system. When you design matrices, you need to be sure that your equations are linearly dependent from one another. Otherwise, your system will end up being underdetermined, and you've got to put in new constraints. And underdetermined systems in and of themselves, unless you do some trickery, will not allow you to calculate all the information that you need. All right, for further reading, read the first part of Chapter 8 in the Stephanopoulos book, from 309 to 333. We will pick up on the metabolic flux analysis, talk about overdetermined and underdetermined systems on Wednesday, and then we will have a flipped class on Friday.